All right, I added this back on to the end of 2.6 because I didn't really cover it, but we absolutely should have. It makes the conversation about the rest of it a little more difficult. So I have actually 3 periodic tables because I don't want to confuse too much of it. All right, so let's talk about the periodic table. We're going to talk about these different sections a little more later, but this section here, okay, so the section that continue this section along with this group here, these are known as the main group. Okay, so those blue guys here are known as the main group, those two together. Good. All right, this group down below between the main group is known as the transition metals. Okay, and again, having a conversation about metals and non-metals, the main group is slightly different. In fact, there's a lot of groups that, chemistry groups that focus on either main group or transition metals. The two remaining main groups that we have, or the two remaining groups that we have, generally we lump them together, but they are actually quite a bit different. The lanthanides and the actinides. Lanthanides and actinides, they're actually really important. We have actually often call both of these the rare earth metals. Usually, actually, just the lanthanide series is typically called the rare earth metals. It's not that they're rare, it's that if I dig up soil, I'm going to get lanthanum, cerium, I'm going to get praseodymium, I'm going to get a bunch of the lanthanide series, but separating them out is really hard to do. So it's really difficult to separate out the lanthanide and actinide series. Okay, good. So those are the different groups on the periodic table. So another one. So let's take a look at the different going up and down. This is known as a group. Going left to right, this is known as a period. And we typically look at periods and we put numbers out front, 1, 2, 3, 4, 5, 6, 7. Notice that this actually should be lanthanide and actinide. Those should be in the D block. So technically over that way would be the lanthanides and actinides. So this is out front of 6. The actinide series is out front of 7. Okay, good. So we have special names for each of these. So this is group. Let me just focus way in on this thing. So we have group 18. This is the new nomenclature. Group 8A or 8A, however you want to look at it. It's either Roman numeral or this is the old way of looking at it. What you'll notice is group 8A. So we have, let's do this way. So I have 1A over here to the left, 2A, 3, 4, 5, 6, 7A, okay? And the B groups are down here, are down in the transition metals, 3B, 4B, 5B, 6B, 7B, 8B, 9B, 10, 11, 12, or 1, 2B. There's a reason behind that. The new nomenclature is a lot better because it kind of makes a little bit more sense. All of these guys act very similarly. In fact, they all kind of have their own properties. So let's move over to, now that we know on tops we have group numbers. So all of these up top are the group numbers. So if I say 13, 3A, or if I say 13 or 3A, I'm talking about that group with boron on the top. Okay. Okay. So each of these has a special name. The one all the way at the end, the one I've highlighted in orange, is known as the noble gases. The one next to it This one is pretty important. We use these quite a bit. And in fact, I use the term quite a bit. Everyone really uses it quite a bit. So be prepared to hear it. This is called the halogens. Used a little bit less, but certainly used. The one next to that. These are known as the chalcogens. So noble gases, halogens, chalcogens, and then we're going to go all the way over to the other side of the periodic table. We have the first group, known as the alkali metals. And the second group. What have I already used yet? Let's try blue. I already used that, whatever. So this other one here is known as the alkali earth metals. There's some other interesting ones as well. These three together, so silver, gold, and copper, these are known as the coinage metals because they're used for coins. Yeah, so coinage metals, but what you're going to notice is down a group, the behaviors are going to be similar. And the question ultimately, why are the behaviors similar down a group? So that takes us to our third and last periodic table. So the group numbers represent the number of valence electrons. Okay, so the number of outer electrons in an atom. Okay, so if we're looking at valence electrons, we have the atom, and then outside of it, it's got a bunch of orbitals, and the electrons are there. We don't really need to talk about that. We will, but ultimately what happens is we have the number of valence electrons is equal to the group number. Okay, the max, by the way, is going to be 8 for the main group. The eight max for the main group. The D block. Okay, so the transition metals can be slightly different than that, but 8 max for the main group. So group 1 has 1 valence electron. Group 2 has 2 valence electron. We're going to skip the transition metals. Group 13, we're just going to ignore the 10 part of it. Okay, so I'm just going to essentially ignore the 10 part of it. 3 valence electrons, 4, 5, 6, 7, and 8. All right, so we can ignore the 10 part of it. So 1, 2, all the way up to 8 valence electrons. So let's talk about this concept of the octet rule. The octet rules is basically saying that 8 electrons in an atom or in an ion or atom is stable. Meaning that our atoms are going to turn into ions because they want to gain electrons. They want to get to that 8 electrons of stability. Okay. If you look at the periodic table, so we had what, 3, 4 electrons, 5, 6, 7, and 8. This final row here is where they really want to get to, because anything with a noble gas configuration has 8 electrons. Okay, so we call these, anything here is going to have noble gas configuration. Ultimately, it has 8 electrons. Doesn't matter what the electron configuration is, what we'll talk about, it has 8 electrons, which is perfect. Okay, so if we take a look at something like magnesium, actually, we'll just make it simpler than that. Let's take a look at sodium. Sodium has 1 valence electron. So sodium has a choice. Sodium can either add electrons. So it can add electrons. That's 2, 3, 4, 5, 6. It can get 7 to get to that argon core, or it can lose the electron to just go back to neon. Okay, so sodium has a choice. It has that 1 valence electron. So do I get rid of the 1 or do I add 7 more? Okay, what is easier to do? If you said lose 1 electron, you would be correct. So sodium and most metals, because they only have a few valence electrons, is going to lose 1 electron. So sodium, we expect to have a charge of +1. Well, if it has a charge of +1, all of those in group 1 have the same charge. So we expect everything in group 1 to have a charge of +1. If we take a look at, let's say, calcium. Calcium has 2 valence electrons, so it has a choice. Calcium has the 2 valence electrons, so it can either gain 1, 2, gain 1, 2, 3, 4, 5, 6 to get to krypton, or it can lose 1, 2 to get back to argon. Again, going for that 8 valence electron core. So we would expect this calcium to lose 2. I'm positive I lost an electron. Group 2 tends to be 2+. Easier to get rid of 2 than to gain 6, right? So group 1 is going to become +1. Group 2 is going to become +2, just because that's the thing that they like to do to get to that stable 8 electron core. Okay. So what we're seeing here is we want to get to 8 electrons. So we are going to have 2 options. 1, we're going to add until I have 8, or I'm going to 2, lose until I have 0, right? Which is basically, when I say 0, it's back to previous, to noble gas core. Okay, so to that noble gas core. So if I lose to 0, I end up at the previous line. I end up back with 8 electrons because I've gotten rid of everything out of that shell. Good. All right, so let's look at the other extreme. So noble gases are happy where they are, but let's take a look at chlorine. Chlorine has 7 valence electrons. So its choices are gain 1 and become argon, or lose 1, 2, 3, 4, 5, 6, 7 to get back to neon. Obviously, it's going to gain 1 electron, assuming it has a source. So we would expect chlorine to have lost 1. If it loses 1 electron, everything in that row is expected to have a -1 charge, because they're all going to have the same electron configuration. They all have 7 valence electrons. Losing 1 is easiest to do. How about oxygen? Well, same exact question. Oxygen has 6 electrons. It would either gain 2, 1, 2, or it would lose 6, 1, 2, 3, 4, 5, 6 to get back to helium. So gaining 2 to get to a neon configuration is easier. So if it gains 2 electrons, it has a total charge of -2. Most things in this row have, well, pretty much everything in that row is expected to have a -2 charge, because it's easy to lose 2 over gaining 6. Okay. Or I'm sorry, gaining 2 over losing 6. Once we get a little bit closer, so if we take a look at nitrogen, and here's where it does feel a little bit different. Nitrogen has a choice. Nitrogen can gain 1, 2, 3, or it can lose 1. It can lose 1, 2, 3, 4, 5. Gain 2, gain 3, or lose 5. So nitrogen can honestly be a -3 or a +5. And both of those things are a possibility for nitrogen, because the closer we get to the center, the harder it becomes. And the center, by the way, is carbon. Okay. Aluminum is one of those ones that is always has the same charge, again, it's going to either gain 1, 2, 3, 4, 5, or lose 1, 2, 3 to get back to the previous. And it does, in fact, gain 3. So aluminum, boron tend to gain 3. It becomes plus 3. Carbon, on the other hand, has, as the final one, carbon has a choice. Carbon can gain 4 or lose 4, become plus 4 or minus 4. Which does it do? Well, it turns out carbon really never forms an ion because all of these are forming charged substances. Carbon just kind of hates that, so it won't do any of that really. So what we notice is things in the middle near carbon, like nitrogen, phosphorus, silicon, arsenic, these tend to have multiple oxidation states. Just like all of these here, they have multiple oxidation states because now 4 electrons, but if you can get out to here, you're stable. If you can get rid of them, you're stable. So all of these guys tend to have multiple oxidation states. So when we are determining charges of different types of compounds, these are the sets of rules that we have. Group 1 and group 2, they will always have +1 and +2 charges, okay? Fluorine is always going to be, oh, that is very wrong. Fluorine will always have a -1, okay? So those are always, okay? Hydrogen is always as well. Hydrogen is always going to be +1, except when bound with a metal where it's -1. Yeah, and then oxygen is mostly, it's pretty much exclusively -2. The only opportunity it's not is where it's in a peroxide, and we're not going to run into peroxide. So oxygen is pretty much always -2. And the last little bit, group 17, those are the halogens, are mostly -1, okay? Yeah, so fluorine takes precedent. The higher halogen tends to take priority. So if you have a bunch of halogens together, the one that's higher in the group will be negative, the lower one will be different. So let's take a look at determining oxidation state from formula. So let's just use an example of KHSO4. So this is about as complicated as it gets. In fact, let's not even start with this one. Let me just move this over. We'll do this one next. Let's just do something simple. SO2. All right. So this is how I want you to think about these compounds. So SO2 is going to be our example. So oxidation states. We're going to have a couple of different spots. On top, this is going to be the atom oxidation state. Whenever I say oxidation state, I essentially mean what is the charge. Right here, you would have the charge of molecule. All right. Below, I am going to put the total atom charge. Let me clarify the top, not the atom oxidation state, or I should say the individual oxidation state. And then I'm going to set a little equal sign here, and this one right here is going to be the total. Basically, it's going to be the charge of the molecule. It's going to be plugged in here. All right, so there is no charge, so we don't, so if there is no charge for this thing, okay, so it's neutral. If there's nothing up there, it's neutral. That also means the whole thing has to be equal to 0. All right, so sulfur and oxygen, which one of those appears in our list? So we always check this in order. So this always goes in order. Do I have anything from group 1? I don't. Do I have anything from group 2? I don't. Do I have fluorine? No. Do I have hydrogen? No. Do I have oxygen? I do have oxygen. So oxygen has an oxidation state of -2 according to the set of rules. All right. So we are going to identify all but one. So once we have one thing unidentified, in this case, sulfur is the only unidentified thing we have. Now we can do the math. So oxygen has -2 charge. but there are two of them. So the total charge, again, the total charge for oxygen is -4, because I've got one more time, -2, each individual oxygen is -2 times the 2 that we have is equal to -4. And the way we think about this is, if I were to ignore all of that other stuff, what has to go in that parentheses to make this true? So once we have all but one identified, we end up with a math problem. What has to go in the parentheses, the empty parentheses, in order to make this true? Okay, so I'll erase this. We need a +4 here, all right? And the best way to think about this is we always start with what we know. We kind of travel around, do total charges, and then we end up with what we don't know. So oxygen is -2, giving me a total charge of -4, +4 plus -4 gives me 0, so it's neutral. And I only have one sulfur, so it's going to take on the full charge, giving me a +4 in the end. I'll use the same color, green, there we go, +4. What is the oxidation state of sulfur? It is +4. Again, we follow those rules. So let's take a look at this one, KHSO4. Again, same exact thing. There is no charge up in this corner, so the whole thing is set equal to 0. It's neutral. So we've got a bunch here. So we have to we have 4 different atoms, different types of elements. We need to identify all but one. We want to bring it down to one that we don't know. So let's go through the list. Do I have anything from group 1? I do. K. Potassium is +1. Okay. And we'll do the total charges in just a second. Do I have anything from group 2? No. Do I have any fluorine? No. Do I have hydrogen? Yes, I do. I have hydrogen. Hydrogen is right here. It is also +1. What's next? Do I have any oxygen? I do. That's going to be -2. And I don't need to go any further because we only have sulfur left. So we need to identify sulfur. So we are going to do the calculation. That is for oxygen plus the charge from all of the sulfur plus the charge from all of the hydrogen plus the charge from all of the potassium. Okay, so I have 1 + 1. I've got 1 potassium at +1, giving me a charge of +1. I have 1 hydrogen at +1, giving me a charge of +1 for hydrogen. In fact, I could probably just get rid of those pluses because they're probably confusing. So, yeah, okay. Sulfur, I don't know yet. So we don't know sulfur yet. We're looking for that one. Oxygen, I have 4 oxygen at -2 each. So 4 times -2 gives me a total charge of -8. So what does sulfur have to be in order to make this whole thing neutral? +6. Okay, so we have to have a +6 charge for sulfur. And there we go. What's the oxidation state of sulfur? +6. Okay, so that's the whole process. Last one. Let's see, change color. Here we go. Fe2O3. So you run into these oxidation states of these quite a bit. Yeah, we'll do 2 more. Okay, so this is what we got. There is no charge, so the whole thing is neutral. We go through our list, and what you're going to notice is oxygen is -2. There are 3 of them for a -6 total charge, or yeah, -6 total charge. Again, we're going to do the math. What has to go there? This is oxygen, this is iron. So we have to put a +6. Iron has to be +6 total, but here's where it is. So it has to be +6, but there are 2 of them. That means that 6 divided by 2, each of them has to come up. The total for iron has to be +6. So each of them is +2, or +3 rather. So the charge of the iron, the oxidation state of the iron is +3. All right, last one. Let's take a look at K. Let's actually just take a look at NO3 minus. So this time we actually have a charge up here. So the total charge for this whole thing is -1. Oxygen is -2 because that's in the list. So my oxygen plus my nitrogen has to come out to -1. So I have a total of 3 oxygens at -2 each. So again, 3 of these times -2 gives me a total charge of -6. What has to go? What has to go in the empty parentheses to make this true? We have to have a +5 in that nitrogen slot to make sure that right, +5 -6 gives me a total charge of -1. So nitrogen has to be +5. So whenever there's a charge there, all you have to do is just set this value to something else. Okay. All right, that's it. So we're going to do these in class and we're going to do a bunch more, but that's the concept there, determining oxidation state. And it's just reading the periodic table properly.